Yeah. So we kind of broke this down, but I want to break it down just a tad further. Yeah, P is prime and Z. Then P remains prime. Actually, look at the notes to show you this right. If P is equal to 11, 13, 17, 19, 5. And we said P, I gave it the status, breaks down. I'm going to make that more precise today. P is equivalent to 1, 3, 7, or 9. Right. Now we noticed actually that, for example, well, look at 19 remains prime. Look at 29. It is possible to write this as x squared plus 5y squared. Namely taking y to be 2 and x to be 3. So this actually gives you a concrete way to break this down. And this actually breaks down into 2 prime. Those irreducibles actually are prime, because actually it's fairly easy to show that because they're enormous. Number 3, we notice we can't break down. Just some of the other ones equivalent to 3 mod 20, right? Other primes come out 23, 43, 83, like this, and you'll find they don't break down. So, or it didn't break down like this. I'll look more carefully. 3, 23, 43, 83. These are primes in this class. Also, I think you will find 7, 47, 67, etc. These are in my breakdowns, right? But you will find that you can't write any of these as a square if it's 5 times a square. That's it out. Right. Notice none of these primes have the property that -5 is a square quantity, right? So why does this? Let me kind of do some more sweeping generalization. Suppose that P like 29 above. So in other words, notice the norm of P is P squared. When can this break down into 2 irreducibles, both norm P, right? Well, what we need is P to equal alpha beta with norm alpha, norm beta equals P, right? Because the norm of this is P squared, so that means the norm of alpha and the norm of beta both have for this to be non-trivial. Everybody okay with that? Well, this means if norm alpha equals P, then and alpha equals, let's say, x plus y radical -5. This means that P is equal to x squared plus 5y. Right, them? Now, reduce this mod 5. So the P has to be a square mod 5. Now let's assume that this is not P itself, it's not 5. Let's assume that P is relevant to the prime 5, and of course we've already taken care of 5 anyway. What does this mean about P? Like the only squares mod 5 are 1, which means that these are both equivalent to 3 mod 4. Right? Because 4 is, of course, divides 20, so you don't have to worry about that. Notice these are both equivalent to 1 mod 4, which is why we get the 29, we can't get this. But notice, so what happens is if we can break this down further, so we can bifurcate this case as well. It's down into 2 irreducibles, it's like 29. What do you suppose happens in this case? What happens in this case is very similar to what we had last time. What happens is, it turns out the ideal generated by P is P T bar, where these are non-principal ideals. For example, we saw last time 3 was 3 where this is P and this is P. So that's kind of an exhaustive list of what happens to primes here. These equivalence classes, they all remain prime. These two, they split into 2 principal prime factors, and these 2 equivalence classes, they actually break down into these kind of ideals. Because actually we've shown that it's impossible really for this to break down into 2 irreducibles going P, and that's what is necessary for that to produce. Okay, any questions? Okay with this? Okay, so I'm gonna spread my wings out a little bit. Let me we're gonna talk about Dedekind domains in a bit, but let me give you all something that I think that many of you are already familiar with. So here's a fact, and we're going to talk about this after we get through evaluation domains a little bit. So the integral closure of these and finite extensions rationals. Any ideal any proper ideal can be written uniquely as a product of so A equals P1 A1 up to L. Actually, this was sort of born out of that attempt at Fermat's theorem. Do y'all remember my amusing historical ditty about the fact that Fermat's theorem would have been proved a long time ago if these particular rings didn't have unique factorization? Well, they came up with this thing called ideal numbers, which was really the precursor of this. It turns out these domains are called, more generally, where you have any non-zero proper ideals, private prime ideals, these are called Dedekind domains. These are integral domains where every non-zero proper ideal can be written as product of prime ideals, and by the way, this decomposition is in fact unique. So from that perspective, you see that this is a nice generalization of the notion of UFT. Actually, more properly, it's a generalization of PID in the following sense. What happens in a UFT? In a UFT, every principle, so we can generalize UFTs in this case. What is true about in a UFT? Every non-zero non-unit is a product of prime element, right? So you're talking about elements here. Every non-zero non-unit is a factor unique to primes. Let me recount that a little bit. Every proper principal ideal, non-zero, proper principal ideal, can be written uniquely as a product of principal prime ideals. Dedekind domains just removes principal from it. So instead of saying UFD, every principal ideal, every proper non-zero principal ideal can be written as a product of principal prime ideals, what you're saying is every ideal that is not zero and proper can be written as a product of prime ideal. We got the principle on the table. And in fact, these ideals are, in a certain sense, very close to being principal, even though they're not. They're very nice. They are, in fact, two generated. Every in a Dedekind domain, in a domain where you have this property, every ideal is two generated. In fact, it's 1.5 generated. Which, what does that really mean? What that means is basically you can put on a blindfold and pick any non-zero element out of the ideal and make that one of the generators, and then the other one you have to choose more carefully, right? So that's the 1.5 generator property. Any non-zero element, and you can kind of pick, you can pick at random, and then anything else you have to adjust it correctly. So these are actually 1.5 generated in that sense. Principal ideals are free R modules, right? In an integral domain, right? A principal ideal is a free R module, right? In a Dedekind domain, all ideals, all non-zero ideals, they're all projective, right? So it's a little bit more general than free. We'll see some of this later. Anyway, so it turns out in a ring of algebraic integers, in fact, more generally in the Dedekind domain, you have any ideal, it can be written uniquely as a product of prime ideals. So this is kind of repairing loss of unique factorization. So for example, if you join the 23rd root of unity to Z, we've discussed the fact that this is not a UFD. I haven't proved it, but I told you that. I'm a pretty believable guy. So this thing is not a UFD, but it is a Dedekind domain. So even though not all its elements factor uniquely into primes, all its ideals factor uniquely into prime ideals. Now, there's a really cool theorem here that I'm going to. Yes.
Sorry, just to clarify, you're talking about how this is a generalization of the UFD. Is the generalization that you say it can be written maybe uniquely as a product of prime principal ideals?
In a Dedekind domain, so in a UFD, a UFD, every non-zero non-unit can be written as a product of primes. So you can restate this way. In a UFD, every proper non-zero principal ideal is a product of principal prime ideals, right? And here you kind of take the principal off the table. It's really more proper to say Dedekind domain is generalization of PIDs because all PIDs are Dedekind domains, but not all UFDs. That principle is a little bit tricky there. Not all PIDs are Dedekind domains, it turns out, but not all UFDs are. So it just generalizes that notion of factorization.
Do you agree with the like? So I remember my master's when I took algebraic number theory course, my professor was like, oh, this is like the reason why ideal is called ideal, because it's the ideal thing you want to think about, but you want to generalize. But I don't know if that's like
Yeah, I mean,
a
ideal.
far stretch or.
Well, I mean, one of the things that's good about ideals is this. So when we talk about factorization, so if any of you heard me talk about factorization is almost always accounts in terms of elements. And you can talk about that in terms of principal ideals if you want, but one of the things that's powerful is if you have a property of a ring that you can couch in terms of its ideals, it's usually a better property, right? And so what happens is a UFD, its factorization properties are in terms of ideals. Every non-zero prime ideal contains a non-zero prime element, right? But as you get more general, oftentimes you get off the ideal path, and that makes it way more like the Wild West, right? There's kind of no rules anymore, sort of. You know? Well, there are rules, but they're harder to find. So here's a theorem. F over Q, and you can generalize this, but I think it's fine for now. The algebraic number field. So, for the purposes of this theorem, I just mean that F is some finite extension Q with ring of integers R. So R is the collection of everything in F that is the root of some monic polynomial of Z. If E and Z minus 0 prime. So suppose you have an ordinary rational prime, then we've actually seen this via example. Okay, no surprises so far if you've got faith, because any ideal should be a product of prime ideals. The EI called ramification. These the power for rings of algebraic integers, these are almost always ones, right? Almost always ones. In fact, only for finitely many primes in the integers can any of these exceed one, which is kind of cool. If so, I'm going to define this new integer, and how am I going to define it? Well, if you look at R mod pi, it's actually pretty easy to see that if you take pi, which is an ideal in R, and you intersect it down to Z, you get exactly this little prime here. So if you look at the field extension, R mod PI, this is a field extension actually, because we're gonna see later, all the PIs that are non-zero primes in a Dedekind domain are maximal. So this is in fact a field. Of course, we know the Z mod P is a field. If you look at this, this is called the degree. Yeah. Just the degree of this field extension. By the way, it's bounded above by the degree of F over Q. Then, if you look at the degree of this extension here, then if you add all these EI, FIs up, the product, you will get the degree of this. Let me make a couple of notes. This theorem. Note number one, if F over Q is Galois, then in the case that this extension F over Q is Galois, then all these ramification indices are all the same across the board. And all the degrees are the same across the board. And in this case, N is equal to EFK. And number two, this is a fact we have not shown yet, but I'll give it to you. For all but finite and many primes, EI equals 1 all I. And in fact, the primes must divide the discriminant. Okay, before I give you an inkling of why this is true, this is kind of neat, right? Because, well, we can see what happens here. Let me give you a simple example. Simple example. Okay, let's take the prime P equals okay, 11 remains prime. Okay. So in this case, what happens is there you go. It's the ideal germ 11 upstairs because it remained prime there. Right? So notice in this case, one. And if you look, this is a field extension of the field of 11 elements, right? Notice that -5 is not a square mod 11, right? That's why 11 came up. So this is a proper extension, right? Because really, this is the smallest field that contains Z11 and the square root of -5. Square root of -5 is not a square in here, so this is a field extension of degree 2. So basically, you can take this polynomial and take take this field and take the polynomial x squared plus 5 and join the root, and you get this, right? And here you go. E1, there's only one prime, and 2 is the degree of the extension, right? Let's do another one. Phi 5ZI. Oops. That's small. So that's this ideal square, right? Now, if you look for the degree here, you know, Z square root -5 modulo the ideal -5. Basically, radical -5 and 5 itself is 0 here, so this is actually 1. Right, because radical -5 is 0, and so all you're left with is the Z part, and that kills 5 as well. So here, 2 times 1, and you got it again. All right. So if we look at, for example, 3, we've seen that work for us. So if you look, if we call this just brevity, E1, then if you look at Z, notice that minus radical 5 mod 3 is the same thing as 1. Right, so again, what happens is this is 1. This field right here is isomorphic to C mod 3. It's only got 3 elements in it. And then you can do a computation check. This one has 3 elements. These 2 primes are distinct, so the ramification is 1 apiece. And what we have here is E1 equals 1, F1 equals 1, and E2 equals 1. F2 equals 1. Because modding by P1 and P2 is the same thing, because these are actually, there's an automorphism that takes this ideal to this ideal, so the quotient should be the same. So what we have now is 1 plus 1 is 2. All right. Right, okay. So that's kind of a demonstration of this. Let me kind of tell you why this works. And then I'm going to give you one that's a little bit more powerful even. I'll show you how to generate these ideals. Okay, you all have all seen the norm map, right? When I did the x squared plus 5y squared, you see it comes from the norm. There's actually another way to do the norm, which is actually equivalent to this, right? It doesn't look like it at first, but so using notation from theorem 524, that is algebraic number field where integers are. if P in R is a non-zero prime. And intersect this prime ideal down to Z. And the intersection, actually, this is a general statement, it's true. If you have an integral domain that contains another integral domain, you have a prime ideal in the big one and you intersect it down to the small one, the intersection is prime. So the only place to go with this is some prime P. Then the norm of the ideal P upstairs is P to the F, where F is the degree of R mod P over Z mod P. So what you probably should verify here is you can do this just by doing kind of a vector space counting argument. Normal P to the opposite. And here's what's easier is if P is not equal to Q or prime, then the norm PQ and in fact, we define the norm on primes, on prime powers, and then we split it up this way, right? So it's easy to see that this definition works out. So to justify this, and in fact, this norm for principal ideals corresponds exactly to the norm you used to. So this generalizes it because these prime ideals here, or more generally, products of prime ideals, do not necessarily have to be principal. But their norm is you just intersect it down and take the product of the ideals that they intersect to the appropriate power. Notice that you're getting, no matter what the ideal here is, you're getting a principal ideal for the norm, even if you take the norm for non-principal, you get principal. So if you start with a principal ideal, you take the norm for principal ideal, you will get a principal ideal, and it will correspond to the usual norm that you're used to. So, for example, the norm, the ideal generated by factor that into primes, and you will actually get, it should be 6, the one that you used to, this times its conjugate. But if you work it out this way, you get what you want. So let P be in Z, not Z. Then the norm is P to the n power, where n is the degree of the extension here. And that's actually easy to see because if you think back to the element-wise view of norm, what you're doing, you're taking the product of conjugates, and there should be n if the degree of the extension is n. In the quadratic case, there's 2 conjugates, et cetera, et cetera. So the norm of P and the norm of P is also equal to the norm of P1, E1, P2, E2, PK, EK. And the assumption is, of course, all these P's are relatively prime. they're different, distinct. So this is norm P1, E1. Up to norm PK, EK. And then we have to use this fact here, which you might think about why that's true. It sounds like homework problem. And this is EK, but each of these is the ideal generated by P, Fi, F1, E1, E, FK, EK, which is P, E1, F1, E2, F2, CK, F2. So there you get it. The exponent n should be the sum of EI, Fi. Okay, any questions on
Are there any like weird things that ain't like a traditional vector space, but are more like a general free module?
that? Now run that by me again.
Like, so we're looking at these things as like vector spaces, right? Sometimes, but you said you
Well, to get this, what you're looking at is you're looking at these things as a vector space over, you're looking at P to the A. So you need to look at P to the A mod P as a vector space over R mod P, right? When you're thinking about how to,
okay.
how to extend the power. Okay. Here, and then I'm gonna show you kind of some neat computational stuff. Okay, I'm gonna use this notation again. Here. Let Q be algebraic, degree n. So just like before, it's an interval extension, and R the ring of integers. And I'm going to show you how to get your hands really on this, on how to generate these prime ideals. Let F equal Q alpha. By the way, there's no loss of generality in this because you have a finite extension of characteristic zero field. It's always a simple extension. So you can always find a single element of F that generates it. And F of X and QX, the minimal polynomial. Let's make it monic. Over ZX. And I'm gonna let alpha be an R. Let me kind of straighten you out a little bit on this because F is Q adjoint of alpha. There's no reason that alpha should be a root of a monic polynomial over R. But again, it's a fraction of things in F. And so you can actually bring it to a denominator where you can reduce this to, you can assume without loss of generality, this is actually something that's an integer. So alpha is an element of R. So in ZP mod PZ x, suppose f of x bar. So what I mean by this is take this, whatever this f of x is. Let's take this f of x and reduce it. So suppose that it factors this way, and maybe my notation is starting to be suggested here. I guess I should put little bars over this. So suppose you factor this mod p, and it's into a product of polynomials. Of course, z mod p is a field, and so this factorization is unique. Then if fi is degree of fi bar of x, and I'm going to show you how to generate this. This is that 1.5 generator property that I was talking about. It turns out it can always be generated by P and Fi of alpha. Actually, no, we're going to. This is not mod p. This is just pull this back to any polynomial that you like that's equivalent to that mod p. Then when the Fi so in other words, you can reduce stuff and basically get everything you want. So let me give you a concrete example of this that I hope will be useful. Actually, I had to do this. I needed this example in my PhD thesis, as a matter of fact. So here's an example. Consider Q alpha, with alpha a root of what is it? X5 minus X cubed. This is a 5th degree extension. It's not Galois. So I needed primes. So I was working on a problem. I need an example of primes broke up. So this is the one I did. So here's my question. Example: what happens to 3 in R, the ring of integers? Well, according to theorem, look at take this over the field of 3 elements and see if you can factor it. And I can't do that this quickly, so fortunately I wrote something down. This is actually x squared check here. This is equal to x squared minus x minus 1 plus x cubed plus x squared plus x minus 1. And let's check that. Notice x5, ding, ding, ding there. I get an x4 minus x4, so hunky-dory so far. For the x3 term, I get 1x3 minus 1x3, so I'm back down to 0, minus x3, so I've got that. Oh, and by the way, this polynomial is irreducible over the rationals. X squared term, I get minus 1, minus 1, minus 1. So I get minus 3x squared, but that's 0, right? And then I get plus x, minus x is 0, minus 1. Right, the only one I had to fudge mod that is the quadratic term that kind of came out of the loop. And it turns out mod 3 that these two polynomials are both irreducible. And that's easy to check. All you got to do is plug in stuff because the polynomials of degree 2 or 3, so if they reduce any further, they have to have a root, right? It's clear that 0 is a root of neither one of these. If you put in 1, it doesn't work. And if you put in -1, it doesn't work. So that one's good to go. If you put in 1 here, that chunk is 0, -1, so doesn't work. And let's see, minus 1, minus 1, minus 1, 0, plus 1. Okay, so these are all irreducible. So the theorem says, so in this ring of integers, if you look at the ideal generated by 3R, this is actually PQ. Two polynomials factors into 2 primes. For emphasis, I'll put this here. And the degrees are well, let me just put it this way. F1 is 2 and F2 is 3. Because what this means is this is an irreducible polynomial over the field of 3 elements. So when you adjoin the root of that, you get a degree 2 extension. That's essentially what that means. This is an irreducible polynomial of degree 3 over z mod 3. So adjoin the root of that, you get a degree 3 extension. And of course, the finite fields are all Galois. So once you adjoin a root of an irreducible, you get everything. So, any questions? By the way, this is not a Galois extension because if it were Galois, the degrees of both of these would have to be the same, and they're not. So you can kind of practice this. You can actually, oh, and actually, I can tell you what the prime P is. It's generated by 3 something, and Q is generated by 3 something. And what it's generated by is plugging in alpha to whatever the polynomial is. So I don't know what alpha is, it's just a root of that, but it should be generated by P should be generated by 3 and alpha squared minus alpha minus 1, whatever that number is. And this should be generated by alpha cubed plus alpha squared plus alpha minus 1. Okay, any questions on it? Okay, I've got kind of a challenge problem for you. Look at this again and try to see what happens to 7 as opposed to 3. So you can get back. Any questions? All right. Well, I hope you've enjoyed this. We're going to get kind of into the integrality and get kind of back into math, but I wanted to give you all a little bit of computational stuff so that you'll have. I like people to be able to do it, so I'm going to ask you some computational problems as well. I don't think the Friday class is going to work out the way I wanted it to because things in Fargo are complicated. So I actually recorded your next class this morning, so I will post that today. You can look at it and talk about it around. Any questions? Only 2 minutes after. I apologize for that. I will see you all on Monday